the most common planets in the universe don't exist in our solar system. You won't find these worlds anywhere near Earth. They represent a cosmic population we completely missed. Tonight we're discovering why half the universe chose a planetary design our neighborhood rejected entirely. Before we dive into these missing worlds, drop a comment about what you think our solar system is lacking. If you enjoy these cosmic mysteries, consider subscribing. These explorations beyond our solar system reveal how strange our home really is. Space telescopes shattered our planetary assumptions completely. A space observatory called Kepler launched with one mission: find planets like Earth orbiting distant stars. Instead, astronomers discovered something nobody predicted. The universe runs on a planetary design we've never seen. These worlds sit exactly where our solar system has nothing. Bigger than Earth but smaller than Neptune. Think about our solar system's planets for a moment. We have small rocky worlds like Earth and Mars. We have giant gas planets like Jupiter and Neptune, but we have absolutely nothing in between those two categories. The universe fills that gap completely. Survey after survey confirms the same shocking pattern. Most star systems contain planets in that missing middle-size range. Our solar system skipped the universe's most popular planetary recipe entirely. Our solar system contains a glaring gap that astronomers never noticed until recently. Between Earth and Neptune lies a size range we completely lack. Earth measures roughly 8,000 miles across. Neptune stretches about 4 times wider. Our solar system contains nothing between those two sizes. But the universe loves filling exactly that space. Planets measuring 2 to 4 times Earth's width dominate star systems everywhere. That's the cosmic real estate our neighborhood avoided entirely. Scientists call these worlds Mini-Neptunes or super-Earths. The names reveal our confusion about what to call them. We never developed proper terminology because we never had any examples to study. This missing middle represents the universe's most popular planetary size class. Our solar system stands out as the weird exception, not the typical example. Planetary surveys deliver the same message repeatedly. These intermediate-sized worlds absolutely dominate the cosmic census. Over half of all known planets fall into this middle category. That's a staggering majority, choosing a design our solar system completely ignored. The numbers keep growing as telescopes find more examples. Every major planet hunting mission confirms the same pattern. Small rocky planets exist. Giant gas planets exist. But the in-between worlds vastly outnumber both categories combined. This discovery forced astronomers to completely rethink planetary formation theories. For decades, scientists used our solar system as the template for how planets should form. 8 worlds ranging from tiny Mercury to massive Jupiter seemed perfectly normal. The universe rejected that template entirely. Our 8-planet system represents a cosmic minority that most star systems never bothered to create. These middle-sized worlds possess something our rocky planets never developed: massive atmospheres made of the same materials that fuel stars. Earth's atmosphere forms a paper-thin layer around our planet. You could drive through its entire thickness in about 20 minutes. These distant worlds wrap themselves in atmospheric shells hundreds of times thicker. The atmospheres contain mainly hydrogen and helium. Those are the lightest, most abundant elements in the universe. Stars burn these same materials in their nuclear furnaces. Rocky planets like Earth never captured such atmospheres during formation. We formed too late or too small to grab those lightweight gases before they disappeared. but planets in that middle size range manage to collect and keep them. This creates worlds that look nothing like anything in our solar system. Rocky cores buried beneath puffy gas envelopes that stretch for thousands of miles. These planets span an enormous range of masses despite their similar sizes. Some weigh twice as much as Earth. Others pack 15 times mass into roughly the same volume. That mass difference determines everything about how these worlds behave. Lightweight versions barely hold onto their atmospheres. Heavyweight champions squeeze their materials into incredibly dense configurations. The variety comes from different formation histories. Some formed close to their stars and lost much of their original material. Others grew far away and migrated inward later. Some accumulated ice and rock in equal measures. Others collected mainly rocky debris. This mass diversity means astronomers can't simply look at one of these worlds and understand them all. Each one represents a different experiment in planetary construction. Our solar system avoided this entire range of possibilities by never producing any examples in the first place. These worlds display puzzlingly low densities that hint at surprising compositions. Many weigh less than they should have made purely of rock or ice. Density works like a cosmic fingerprint for planets. Pure rock creates high-density worlds. Ice mixtures produce medium densities. Gas-rich planets show very low densities. Many of these intermediate worlds fall into that low-density category. This suggests they contain substantial amounts of lightweight materials mixed throughout their structure. Not just thin atmospheric shells, but lightweight components distributed through their entire bulk. Some might be water worlds with vast oceans beneath their atmospheres. Others could contain significant amounts of hydrogen and helium mixed into their solid components. Still others might have super puffy atmospheres that make the entire planet appear inflated. These low densities tell us these worlds formed under very different conditions than anything in our solar system experienced. Most of these planets live incredibly close to their host stars. They complete full orbits in just days or weeks rather than months or years. Our Earth takes 365 days to circle the Sun once. Mars needs nearly 2 Earth years. But these distant worlds often finish their year-long journey in less time than a single Earth week. This proximity creates scorching surface conditions. Stellar radiation bombards these worlds with intense heat and energy. Their atmospheres reach temperatures of hundreds or thousands of degrees. Such extreme orbital configurations challenge our understanding of planetary formation. How did these worlds end up so close to their stars? Did they form there originally? Or did they migrate inward from more distant birthplaces? The close orbits also make these planets much easier for our telescopes to detect. When they pass in front of their stars, they block more light and create stronger signals than distant planets would. Astronomers can't agree on what to call these worlds. The terminology changes depending on which research team discovered them and how they measure their properties. Super-Earth suggests they're just bigger versions of our home planet. Sub-Neptunes implies they're smaller versions of our ice giant. Mini-Neptunes treats them as scaled-down gas planets. Each name emphasizes different aspects of their nature. The naming confusion reflects a deeper scientific uncertainty. These worlds don't fit neatly into the categories we develop by studying our solar system. They represent something genuinely new that requires new terminology. Some astronomers prefer size-based names. Others favor composition-based classifications. Still others group them by their formation mechanisms or orbital characteristics. This linguistic chaos demonstrates how unprepared our planetary science was for discovering entirely new categories of worlds. Intense stellar radiation transforms these worlds into furnaces. Their close orbits subject them to energy bombardment that creates extreme temperature conditions. Surface temperatures often exceed 1,000 degrees Fahrenheit. Some reach several thousand degrees on their star-facing sides. This creates atmospheric conditions unlike anything in our solar system. The heat drives complex atmospheric chemistry. Molecules break apart and recombine in exotic ways. Clouds might form from vaporized metals or silicon compounds rather than water droplets. Some worlds become tidally locked to their stars. One side faces permanent day, while the other experiences eternal night. This creates dramatic temperature differences between hemispheres and drives powerful atmospheric circulation patterns. These extreme conditions make direct surface observations extremely challenging. Most of what we know comes from analyzing the light that filters through their atmospheres during transit observations. Advanced measurement techniques finally revealed this hidden planetary population. Space telescopes developed the precision needed to detect tiny changes in stellar brightness. When planets pass in front of their stars, they block minuscule amounts of light. Early telescope technology couldn't measure such small brightness variations reliably. The signals were too weak and the background noise too strong. Modern space observatories changed everything. They can measure brightness changes smaller than 0.01%. This precision breakthrough opened up an entirely new realm of planetary discovery. Ground-based telescopes also contributed through improved measurement techniques. Automated survey systems scan thousands of stars simultaneously, looking for the telltale brightness dips that indicate transiting planets. This technological revolution continues advancing. Each new generation of telescopes finds smaller planets around more distant stars with greater precision. These discoveries force us to reconsider our solar system's place in the cosmic order. We are not the typical example of planetary system architecture. Our neat arrangement of 4 rocky inner planets and 4 giant outer planets represents an unusual configuration. Most star systems contain worlds our neighborhood never produced. This raises profound questions about planetary formation theories. Why did our solar system skip the universe's most popular planetary design? What conditions prevented us from forming any intermediate-sized worlds? Perhaps our solar system represents a special case rather than the general rule. Maybe the presence of life on Earth results partly from our atypical planetary architecture. These alien worlds are rewriting the textbook on how planetary systems form and evolve. They're showing us that the universe creates planets in ways we never imagined possible. A specific radius determines whether planets stay rocky or become atmospheric monsters. At exactly 1.7 times Earth's radius, something fundamental changes in planetary nature. This measurement represents one of astronomy's most important discoveries. Below this threshold, worlds behave like bigger versions of Earth. Solid surfaces dominate. Thin atmospheres cling weakly to rocky shells. Cross that invisible boundary, and everything transforms. Planets suddenly possess the gravitational strength to capture and hold massive gas envelopes. The same materials that fuel stars become permanent atmospheric components. This size threshold separates 2 completely different species of worlds. Rocky planets that resemble Earth versus gas-wrapped giants that have no solar system equivalent. The 1.7 Earth radius line functions as a cosmic dividing wall that determines planetary destiny from the moment of formation. Two planets can weigh exactly the same, but appear dramatically different sizes. The presence or absence of a thick atmosphere determines everything about planetary appearance. Imagine two worlds, each containing the same amount of rocky material. One formed without capturing any atmospheric gases. It remains small and compact. The other collected a puffy hydrogen shell during formation. The gas-free world appears as a dense, Earth-like sphere. The atmosphere-wrapped version balloons outward to several times that diameter. Same mass, completely different radius. This creates confusion for astronomers trying to classify distant worlds. Size measurements alone can't reveal whether planets are rocky super-Earths or inflated mini-Neptunes. The atmospheric envelope acts like cosmic packaging that completely disguises the actual planetary contents hidden beneath. Planet composition changes systematically as size increases. Small worlds cook up rocky recipes. Large worlds blend ice and gas into cosmic smoothies. The smallest planets in this size range concentrate rocky materials in their cores. Iron and silicate minerals dominate their bulk composition. They resemble scaled-up versions of terrestrial worlds. As planets grow larger, water ice becomes increasingly important. These intermediate worlds contain substantial ice fractions mixed throughout their structure. Not just surface ice, but ice integrated into their fundamental architecture. The largest examples transition toward gas-dominated compositions. Hydrogen and helium contribute significant portions of their total mass. They start resembling the atmospheric composition of giant planets. This composition gradient reveals different formation environments and histories across the size spectrum. Larger planets weigh much less per unit volume than smaller ones. This systematic density decrease reveals something surprising about planetary construction. Density measures how much material gets packed into each cubic mile of planetary volume. High density means tightly compressed materials. Low density indicates puffy, inflated structures. As planets grow from Earth-sized to Neptune-sized, their average density drops dramatically. This happens because lightweight atmospheric components increasingly dominate their total volume. Small rocky worlds pack dense materials efficiently. Larger worlds wrap those dense cores in increasingly voluminous but lightweight gas shells. The result appears like cosmic balloons filled with heavy centers. This density pattern provides crucial clues about internal planetary architecture that telescopes cannot observe directly. A strange absence appears in planetary size surveys. Worlds measuring between 1.5 and 2 Earth radii show up far less frequently than expected. Astronomers call this the Fulton Gap after the scientist who first noticed the pattern. It represents a size range that nature seems to avoid creating or maintaining. This gap suggests something removes planets from this specific size category. Either formation processes skip this range entirely, or evolutionary mechanisms shrink larger planets down past this zone. The gap appears most prominently around Sun-like stars. Different stellar environments might fill in this mysterious empty space through different planetary evolution pathways. This absent population tells us something important about the forces that shape planetary systems after formation completes. High-energy radiation from host stars actively sculpts planetary sizes by removing atmospheric material. X-rays and ultraviolet light heat planetary atmospheres until gas escapes into space. This process works like a cosmic blowtorch aimed at planetary atmospheres. Intense stellar radiation pumps energy into atmospheric particles until they move fast enough to escape gravitational capture. The effect creates two distinct planetary populations. Worlds close enough to their stars lose most atmospheric material and shrink toward rocky configurations. More distant planets retain their gas envelopes. This radiation-driven evolution explains why the size distribution shows clear separations rather than smooth transitions. Planets get pushed toward either the small rocky category or the large gaseous category. Stellar blow-off creates the observed gaps in planetary size distributions by eliminating intermediate configurations. Planets gradually lose internal heat and contract over cosmic timescales. This thermal evolution slowly changes planetary sizes throughout their lifetimes. Newly formed planets contain enormous amounts of leftover heat from their violent formation processes. This internal energy keeps atmospheric layers expanded and puffy. Over billions of years, planets radiate this heat away into space. As internal temperatures drop, atmospheric layers compress and contract. The planet physically shrinks in response. This contraction happens incredibly slowly by human standards, but represents significant size changes over geological time. A planet might shrink by 20% or more during its lifetime. Thermal evolution means planetary sizes change continuously throughout cosmic history, complicating attempts to understand formation processes. The hydrogen-helium envelope surrounding these worlds determines their fundamental characteristics. This lightweight outer shell controls atmospheric properties, thermal behavior, and observable features. Hydrogen and helium represent the universe's most abundant elements. They're the same materials that power stellar fusion and compose most of cosmic matter. These envelopes can range from thin wisps barely detectable by our instruments to massive shells containing more material than entire rocky planets. The envelope mass fraction determines whether worlds behave more like super-Earths or mini-Neptunes. Even small changes in envelope mass create dramatic differences in planetary properties. A shell containing just 5% of the total planetary mass can double the world's apparent size. This hydrogen-helium packaging fundamentally distinguishes these worlds from anything our solar system contains. The solid core buried beneath thick atmospheres controls whether planets can hold onto their gas envelopes. Core size determines the gravitational grip that keeps lightweight materials from escaping. These rocky cores resemble scaled-up versions of terrestrial planets. They contain the same iron-nickel centers and silicate rock mantles that characterize Earth-like worlds. But core mass makes all the difference for atmospheric retention. Larger cores generate stronger gravitational fields that more effectively capture and hold hydrogen-helium envelopes. Small cores struggle to retain lightweight gases, especially when stellar radiation heats atmospheric layers. Large cores maintain firm gravitational control even under intense stellar bombardment. The core-to-envelope mass ratio determines whether these worlds evolve toward rocky super-Earth configurations or puffy mini-Neptune appearances. Current astronomical techniques cannot definitively distinguish between different types of intermediate-sized planets. The same observational data fits multiple internal structure models. Telescopes measure planetary mass and radius with impressive precision, but those two measurements alone cannot uniquely determine internal composition and structure. A dense rocky world with a thin atmosphere produces identical observational signatures to a fluffy world with a massive gas envelope. Both combinations can yield the same mass and radius measurements. This degeneracy problem means astronomers often cannot tell whether they're observing super-Earths or mini-Neptunes. The uncertainty extends to most planets in this size range. Future space missions with advanced instruments will need to break this observational deadlock and reveal the true nature of these mysterious intermediate worlds. Where do these massive atmospheres actually come from? The answer lies in the chaotic environments where planets first form. During planetary formation, baby planets grow inside vast clouds of gas and dust. These stellar nurseries contain the same materials that eventually become stars. Hydrogen and helium dominate everything. Rocky planetary cores form first from colliding solid particles. But if these cores grow large enough quickly enough, they begin stealing gas directly from the surrounding cloud. This theft happens before the stellar wind blows away all the leftover formation materials. Planets get one chance to grab these lightweight gases while they're still available. The atmospheres we observe today represent ancient theft from the stellar nursery that disappeared billions of years ago. These atmospheric shells vary enormously in how much they contribute to total planetary mass. Some barely register as cosmic whispers. Others dominate the entire world. Atmospheric mass fraction measures what percentage of the planet consists of hydrogen, helium gas versus solid materials. This ratio controls everything about planetary behavior. Lightweight atmospheres contribute just a few percent of total planetary mass. They create thin shells around predominantly rocky worlds. Heavy atmospheres can contain 30% or more of the planet's total material. This enormous range means astronomers can't assume anything about atmospheric properties from basic planetary measurements. Two similar-sized worlds might have completely different atmospheric compositions. The mass fraction determines whether planets behave more like super-Earths or mini-Neptunes despite appearing similar from a distance. Atmospheric pressure increases dramatically with depth in ways that dwarf anything Earth experiences. The pressure gradient creates extreme conditions throughout these thick atmospheric shells. Pressure measures the weight of overlying atmospheric layers pressing down at any given altitude. On Earth, atmospheric pressure changes gradually as you climb mountains or dive underwater. These thick atmospheres create pressure changes that span many orders of magnitude. Surface pressures might resemble Earth's atmosphere, but deep atmospheric layers experience pressures comparable to the bottom of Earth's deepest ocean trenches. This exponential pressure increase compresses atmospheric materials and changes their physical properties. Gases behave more like liquids under extreme pressure conditions. The pressure gradient creates distinct atmospheric layers with completely different physical and chemical characteristics. Complex temperature structures develop throughout these thick atmospheres. Heat from the star above and internal planetary energy below create complicated thermal architectures. Temperature profiles describe how hot or cold different atmospheric layers become. Simple atmospheres show predictable temperature patterns. These thick atmospheres develop much more complex thermal structures. Stellar radiation heats upper atmospheric layers from above. Internal planetary heat warms lower layers from below. Convection and radiation transport energy between different altitude zones. The result creates temperature inversions, thermal gradients, and circulation patterns that vary dramatically with altitude and location. This thermal complexity drives atmospheric dynamics and determines which chemical reactions can occur at different altitude levels. Tiny amounts of water vapor and methane determine most of what we can observe about these distant atmospheres. These minority components create the spectral fingerprints that reveal atmospheric composition. Opacity sources are molecules that absorb specific colors of light passing through atmospheric layers. Hydrogen and helium barely interact with light, making them nearly invisible to our telescopes. But trace amounts of heavier molecules create strong absorption features. Water vapor absorbs infrared light at specific wavelengths. Methane creates distinctive absorption patterns in near-infrared observations. Even though these molecules represent less than 1% of atmospheric composition, they dominate everything telescopes can measure about these worlds. The trace components act like cosmic billboards advertising atmospheric conditions that the dominant gases keep completely hidden. Convection zones develop in atmospheric regions where hot materials rise and cool materials sink in continuous circulation patterns. This atmospheric churning transports heat and mixes chemical compositions. Convection works like cosmic cooking. When atmospheric layers come unstable due to temperature differences, hot gas bubbles rise while cool gas sinks to replace them. These circulation patterns occur primarily in lower atmospheric layers where internal planetary heat creates strong temperature gradients. Rising hot gas carries energy upward while sinking cool gas transports it back down. The convective mixing also redistributes chemical components throughout atmospheric layers. Molecules produced at one altitude level get carried to completely different pressure and temperature environments. This atmospheric stirring creates uniform compositions within convective zones while maintaining sharp boundaries between different atmospheric layers. Radiative zones develop where energy transport occurs through radiation rather than physical gas movements. These stable atmospheric layers maintain distinct chemical compositions without mixing. Radiation transport moves energy through electromagnetic waves rather than physical material motion. Photons carry heat from hot regions to cold regions without moving atmospheric gases. Upper atmospheric layers typically become radiative zones because temperature gradients remain stable. Hot gas doesn't become buoyant enough to drive convective circulation patterns. This creates sharply stratified atmospheric structures. Different altitude levels maintain distinct temperatures, pressures, and chemical compositions without mixing between layers. The radiative zones often contain temperature inversions, where upper layers become hotter than lower layers due to stellar heating effects. Cloud formation occurs when atmospheric components reach specific combinations of temperature and pressure that allow vapor condensation. Different molecules condense at different atmospheric levels. Condensation happens when gas phase molecules cool enough or experience enough pressure to transform into liquid droplets or solid particles. Water vapor might condense into cloud droplets at moderate atmospheric depths. Exotic materials like silicate vapors or metal compounds could form clouds at much higher temperatures deeper in the atmosphere. These cloud layers create distinct altitude zones with different optical properties. Some atmospheric regions remain clear, while others become completely opaque due to dense cloud formation. The altitude where different materials condense depends on atmospheric temperature and pressure profiles, creating complex cloud layer structures. Atmospheric composition variations change the fundamental fluid properties that control gas circulation patterns. Different molecular weights create different atmospheric behaviors. Mean molecular weight measures the average mass of atmospheric particles. Light molecules like hydrogen create low-density gases. Heavier molecules like water vapor increase atmospheric density significantly. When atmospheric composition changes with altitude or location, the fluid dynamics change accordingly. Heavy molecular regions sink relative to light molecular regions, driving circulation patterns. These composition-driven density differences can either enhance or suppress convective circulation depending on how molecular weight varies with altitude. The molecular weight gradient becomes another factor, controlling atmospheric mixing and energy transport throughout these complex atmospheric systems. Atmospheric density decreases predictably with altitude according to a characteristic distance called scale height. This fundamental parameter depends on temperature and gravitational strength. Scale height measures the altitude range over which atmospheric density drops to about 1/3 of its original value. Hot atmospheres have large scale heights. Cold atmospheres compress into smaller vertical distances. Planetary gravity also controls scale height. Strong gravity compresses atmospheres into thin vertical layers. Weak gravity allows atmospheres to extend over large altitude ranges. For these mini-Neptune worlds, scale heights typically measure hundreds of miles. This means atmospheric density changes significantly over altitude ranges comparable to entire terrestrial planets. The scale height determines how much atmosphere exists at different altitudes and controls the pressure gradient that drives atmospheric dynamics. Thermal inversions occur when upper atmospheric layers become hotter than lower layers. This reverses the normal temperature pattern and creates unusual atmospheric conditions. Normally, planetary atmospheres cool with altitude as you move away from internal heat sources, but intense stellar radiation can heat upper atmospheric layers enough to reverse this pattern. Strong stellar heating creates temperature inversions where the atmospheric temperature increases with altitude instead of decreasing. This happens when stellar energy deposition exceeds atmospheric cooling rates. Temperature inversions suppress convective circulation because hot gas already sits above cool gas in stable configurations. This creates very different atmospheric dynamics than normal temperature gradients. These inverted temperature profiles occur most commonly on planets orbiting very close to their host stars, where stellar heating dominates atmospheric thermal structure. Chemical equilibrium establishes which molecular combinations remain stable under specific temperature and pressure conditions. Different atmospheric environments favor completely different chemical compositions. Chemical reactions occur continuously throughout these atmospheres as molecules break apart and recombine in response to local conditions. Temperature and pressure determine which reactions proceed and which products remain stable. Hot atmospheric regions favor simple molecules that resist thermal breakdown. Cool regions allow complex molecules to form and persist. High-pressure zones promote different reaction pathways than low-pressure environments. The chemical equilibrium shifts continuously throughout atmospheric layers as temperature and pressure conditions change with altitude. This creates altitude-dependent composition variations. Understanding chemical equilibrium helps astronomers predict which molecules should exist at different atmospheric levels and interpret the spectral signatures that telescopes observe. Planet formation follows a specific sequence that determines which worlds can capture thick atmospheres. Solid cores must form first before any gas collection can begin. Core accretion represents the standard model for building these intermediate-sized worlds. Rocky materials clump together first through countless collisions between solid particles. These growing cores reach a critical size threshold where their gravitational pull becomes strong enough to attract surrounding gas. Only cores that grow large enough quickly enough can steal atmospheric materials from the stellar nursery. The timing becomes crucial for atmospheric capture. Cores must reach sufficient mass while gas still remains available in the formation environment. This two-stage process explains why only some planets develop thick atmospheres while others remain as bare rocky worlds throughout their lifetimes. Small particles naturally migrate toward forming planetary cores through gas drag forces. This process accelerates core growth beyond what simple collision rates could achieve. Pebble accretion describes how millimeter-sized dust grains get swept toward growing planetary cores. Gas in the stellar nursery creates headwinds that slow down these small particles. The gas drag causes pebbles to lose orbital energy and spiral inward toward the central forming core. This creates a steady stream of solid material feeding core growth. This drift process can build planetary cores much faster than traditional collision-based growth models predict. Cores grow large enough to capture atmospheres before the stellar nursery disperses. The pebble drift mechanism explains how planets can form quickly enough to acquire the massive atmospheres we observe today. Stellar nurseries don't last forever. The gas and dust that enable atmospheric capture vanishes after a few million years, setting strict deadlines for planet formation. Gas disk lifetime measures how long stellar winds and radiation take to blow away all the leftover formation materials. Most young star systems clear out within 5 million years. Planets get this limited window to form cores and capture atmospheres before all the raw materials disappear. Miss this deadline, and atmospheric capture becomes impossible. Different stellar environments provide different formation timescales. Some stars disperse their nurseries faster than others, affecting which planets can develop thick atmospheres. This time limit explains why atmospheric capture represents such a narrow window in planetary formation history. Many of these worlds didn't form where we observe them today. Gravitational interactions with formation materials dragged them inward from more distant birthplaces. Migration processes occur when forming planets exchange orbital energy with the surrounding gas disk. This gravitational interaction typically moves planets toward their host stars. Young planets create spiral waves in the surrounding gas disk. These waves carry away orbital energy, causing planetary orbits to decay inward over time. The migration rate depends on planetary mass and disk properties. Some worlds migrate quickly and end up very close to their stars. Others move more slowly and retain distant orbits. This inward drift explains why so many intermediate-sized planets orbit much closer to their stars than similar-sized objects in our solar system. Once planetary cores grow large enough, atmospheric capture accelerates dramatically. The process shifts from gradual growth to explosive gas accumulation. Runaway growth occurs when gravitational attraction becomes strong enough to overcome gas pressure resistance. This happens around 10 Earth masses for typical formation conditions. Below this threshold, cores struggle to hold on to captured gas against the outward pressure from stellar heating. Above this threshold, gravity dominates and gas accumulation accelerates rapidly. The runaway phase can double or triple planetary mass within just a few 100,000 years. This explains how planets acquire such massive atmospheric envelopes. Critical mass represents the boundary between rocky super-Earths and gas-rich mini-Neptunes in planetary formation scenarios. Planet formation doesn't stop once cores and atmospheres assemble. Continued bombardment by smaller objects adds materials throughout planetary lifetimes. Late veneer processes involve impacts from asteroids and comets that occurred after primary formation completed. These collisions deliver volatile materials, including water and atmospheric gases. The bombardment continues for billions of years after initial planetary assembly. Each impact adds small amounts of material while potentially altering atmospheric composition. Some of the atmospheric components we observe today might result from this late delivery rather than original formation processes. Water vapor and other volatiles could accumulate over cosmic time. This ongoing material addition complicates attempts to understand original formation conditions from current atmospheric observations. Some of these worlds might have formed exactly where they currently orbit. This challenges assumptions about planetary migration being universal. In situ formation proposes that planets can grow from local materials without requiring long-distance migration from outer regions. Sufficient solid material existed even in inner system regions. Evidence for local formation includes chemical composition signatures that match expected local formation environments. Migration scenarios predict different composition patterns. The debate continues over which formation mechanism dominates. Some systems might favor in situ formation, while others rely heavily on migration processes. Local formation would simplify planetary system architecture by eliminating the need for complex migration histories. Many of these worlds might have formed in cold outer regions before migrating inward. This formation scenario creates planets rich in water ice and other frozen materials. Water world scenarios propose that planets formed beyond the snow line where water freezes into solid ice. These ice-rich worlds then migrated inward toward their host stars. The inward migration subjects ice-rich planets to increasing stellar heating. Surface ice layers might melt to create deep ocean worlds with thick atmospheric shells. This formation pathway could produce planets with fundamentally different internal structures than anything in our solar system. Massive water layers sandwich between atmospheric shells and rocky cores. The water world model explains why some intermediate-sized planets show densities consistent with significant ice fractions throughout their structure. High-energy stellar radiation continues reshaping these worlds long after formation completes. This ongoing process determines final planetary sizes and atmospheric properties. Photoevaporative sculpting occurs when intense stellar radiation heats atmospheric layers until gas escapes into space. This removes atmospheric material and shrinks planetary sizes over time. The sculpting process operates continuously throughout planetary lifetimes. Planets closer to their stars experience stronger radiation and lose atmospheric material faster. This evolution can completely transform planetary characteristics. Mini-Neptunes might evolve into super-Earths by losing their atmospheric envelopes entirely. Stellar sculpting explains why we observe distinct planetary populations rather than smooth size distributions across the intermediate range. Orbital mechanics can generate internal heat that affects long-term planetary evolution. Elliptical orbits create tidal forces that squeeze and stretch planetary materials. Tidal heating occurs when gravitational forces from the host star vary throughout elliptical orbital paths. This flexing generates internal heat, similar to kneading bread dough. The internal heating affects atmospheric evolution by providing additional energy sources beyond stellar radiation. Heated atmospheres expand and become more susceptible to atmospheric loss. Tidal heating also influences internal structure evolution by affecting core mantle differentiation and geological activity. The additional energy source can drive internal convection and melting. This gravitational heating represents another factor complicating attempts to understand how these planetary systems evolve over cosmic time. These worlds continue evolving throughout their multi-billion-year lifetimes. Atmospheric properties change dramatically over geological timescales. Atmospheric evolution involves multiple processes operating simultaneously over cosmic time. Stellar radiation removes atmospheric material. Internal cooling contracts atmospheric layers. Chemical reactions alter composition. The evolution timescales span billions of years, making direct observation impossible. Astronomers must infer evolutionary histories from current atmospheric properties. Different evolutionary pathways can produce similar current atmospheric states. This makes determining formation and evolution histories challenging from observational data alone. Long-term atmospheric evolution means these worlds represent snapshots of ongoing processes rather than static end products of formation. Individual gas molecules can achieve escape velocity and leave planetary atmospheres permanently. This happens when atmospheric particles move fast enough to overcome gravitational binding. Jean's escape describes the process where fast-moving molecules in atmospheric layers break free from planetary gravity. It's named after the physicist who first calculated how this molecular escape works. Temperature determines molecular speeds throughout atmospheric layers. Hotter atmospheres contain more fast-moving particles that can reach escape velocity. Lighter molecules like hydrogen move faster than heavier molecules at the same temperature. The escape rate depends on how many molecules exceed the critical speed needed to escape gravitational capture. Planets with weak gravity or hot atmospheres lose material faster through this process. This molecular escape operates continuously throughout planetary lifetimes, gradually reducing atmospheric thickness over billions of years. Extreme heating can transform atmospheric loss from individual molecular escape into massive gas outflows. This creates atmospheric rivers that stream away from planets into space. Hydrodynamic escape occurs when stellar heating pumps so much energy into atmospheric layers that gas flow becomes like water flowing from a faucet. The entire atmosphere participates in organized outflow patterns. This process requires much more intense heating than simple molecular escape. Surface temperatures must reach thousands of degrees to drive hydrodynamic outflow from planetary atmospheres. The gas flow resembles wind patterns but operates on planetary scales. Hot atmospheric material streams away from the planet while cooler material flows upward to replace it. Hydrodynamic escape can remove atmospheric material millions of times faster than individual molecular escape processes. Stellar radiation at extreme ultraviolet and X-ray wavelengths delivers enormous energy to planetary atmospheres. This high-energy bombardment heats atmospheric layers to temperatures exceeding 10,000 degrees. XUV heat stands for extreme ultraviolet radiation that carries much more energy per photon than visible light. This radiation penetrates deep into atmospheric layers and deposits energy throughout the gas. Young stars produce much stronger XUV radiation than older stars like our Sun. This means planets around young stars experience more intense atmospheric heating and faster atmospheric loss. The heating process breaks apart molecules and strips electrons from atoms, creating hot plasma in upper atmospheric layers. This ionized gas responds differently to magnetic and gravitational forces. XUV heat represents the primary energy source that drives rapid atmospheric escape from planets orbiting close to their host stars. Astronomers can calculate exactly how much atmospheric material planets lose each second. This mass loss rate determines whether planets retain their atmospheres over cosmic time. Mass loss rate measures the amount of atmospheric material flowing away from planets per unit time. Scientists express this in units like tons per second or Earth masses per billion years. The calculation depends on several factors: stellar radiation intensity, planetary mass, atmospheric composition, and orbital distance all influence the final loss rate. Typical loss rates for close orbiting planets range from millions to billions of tons per second. These numbers sound enormous, but represent tiny fractions of total atmospheric mass for massive mini-Neptune atmospheres. Understanding mass loss rates helps astronomers predict which planets will evolve into bare rocky worlds versus those that retain atmospheric envelopes. Stellar winds carry high-speed charged particles that collide directly with planetary atmospheres. These particle impacts can physically remove atmospheric material through momentum transfer. Stellar wind interaction works like cosmic sandblasting. Fast-moving protons and electrons from the host star slam into atmospheric particles and knock them away from the planet. The interaction strength depends on stellar wind properties and planetary magnetic field characteristics. Strong stellar winds create more intense bombardment. Weak planetary magnetic fields provide less protection. This process operates independently of atmospheric heating. Even cool atmospheric layers can lose material through direct particle impacts from stellar wind bombardment. The particle removal becomes especially important for planets lacking strong magnetic fields that could deflect incoming stellar wind particles. Planetary magnetic fields can dramatically reduce atmospheric loss rates by deflecting harmful stellar radiation and particle bombardment. This magnetic protection determines which worlds retain their atmospheres. Magnetic protection works by creating invisible barriers around planets that redirect charged particles away from atmospheric layers. The magnetic field deflects stellar wind particles before they can impact atmospheric materials. Planets generate magnetic fields through internal dynamo processes involving liquid metal cores. Not all planets develop strong magnetic fields, leaving some worlds completely exposed to stellar assault. Earth's magnetic field demonstrates how effective this protection can be. Our magnetosphere deflects most solar wind particles and reduces atmospheric loss to negligible levels. Planets without magnetic protection lose atmospheric material orders of magnitude faster than magnetically protected worlds under identical stellar conditions. Planets gradually lose internal heat over billions of years, causing their atmospheres to contract and become more vulnerable to escape processes. This thermal evolution connects internal planetary cooling to atmospheric loss. Thermal evolution describes how planetary temperatures change over cosmic time as internal heat sources decay and energy radiates away into space. Cooling affects both solid planetary interiors and gaseous atmospheric shells. As internal temperatures drop, atmospheric layers contract and compress. This compression increases atmospheric density near planetary surfaces while reducing the height of extended atmospheric regions. The cooling process also reduces internal energy sources that help maintain atmospheric expansion. Less internal heat means less support against gravitational compression of atmospheric layers. This thermal shrinkage makes atmospheres more gravitationally bound and potentially reduces escape rates, but also concentrates remaining atmospheric material into smaller volumes. High-energy particles can directly knock atmospheric molecules into space through collision impacts. This atmospheric stripping operates through momentum transfer rather than thermal heating. Atmospheric stripping occurs when energetic particles from stellar radiation or stellar wind carry enough momentum to physically eject atmospheric molecules upon impact. It's like cosmic billiard balls knocking atmospheric material away. The process works most effectively on light atmospheric components like hydrogen and helium. Heavy molecules require more energetic impacts to achieve escape velocity. Ultraviolet photons and high-speed stellar wind particles represent the primary agents driving atmospheric stripping. Each impact transfers momentum that can accelerate atmospheric molecules beyond escape velocity. This direct removal mechanism operates continuously and can gradually erode atmospheric envelopes even without significant atmospheric heating. Current atmospheric loss rates allow astronomers to calculate how long planets need to lose their entire atmospheric envelopes. This evaporation timescale varies enormously between different worlds. Evaporation timescale represents the time required for atmospheric loss processes to remove all gaseous material from a planetary atmosphere. This calculation assumes current loss rates remain constant over time. Some planets orbiting very close to their stars show evaporation timescales of just a few million years. Others retain their atmospheres for many billions of years despite ongoing loss processes. The timescale calculation helps identify which observed planets represent transitional objects currently losing their atmospheres versus stable configurations that maintain atmospheric equilibrium. Comparing evaporation timescales to stellar ages reveals which planets formed with much thicker atmospheres that have since been partially stripped away. Atmospheric escape processes can completely eliminate certain types of planets from specific orbital regions. This creates planetary deserts where entire categories of worlds become extinct. Desert formation occurs when atmospheric loss rates exceed atmospheric retention capabilities for all planets in specific size and orbital ranges. The affected regions become empty of certain planetary types. These empty zones appear in planetary surveys as gaps where specific combinations of planetary size and orbital distance show very few examples. The missing populations reveal where atmospheric escape dominates planetary evolution. Different stellar environments create different desert patterns. Hot stars produce larger desert regions than cool stars because they generate more intense atmospheric heating. The desert boundaries help astronomers understand the balance between atmospheric retention and atmospheric loss across different planetary system architectures. Distant planets reveal their sizes when they pass directly in front of their host stars. This creates measurable shadows that astronomers can detect from Earth. Transit photometry measures the slight dimming that occurs when planets block small portions of stellar light. The technique works like watching shadows move across a bright lamp from far away. The amount of light blocked depends directly on planetary size. Larger planets create deeper shadows. Smaller planets produce barely detectable dimming events. Astronomers measure brightness changes as small as 0.01% to detect Earth-sized worlds around distant stars. This requires incredibly precise instruments and careful data analysis. The shadow method has discovered thousands of planets and remains our most successful technique for finding worlds orbiting other stars. Stars don't remain perfectly stationary when orbited by massive planets. The gravitational pull creates tiny wobbles that betray the presence of invisible planetary companions. Radial velocity measurements track how fast stars move toward or away from Earth by analyzing changes in their light spectra. This technique uses the Doppler effect that also changes the pitch of ambulance sirens. The wobble amplitude reveals planetary mass. Heavier planets create larger stellar wobbles. The wobble period indicates orbital distance and planetary year length. Combining radial velocity measurements with transit observations provides both planetary mass and size. This combination allows astronomers to calculate planetary density and infer internal composition. The wobble method works best for massive planets orbiting close to their stars, making it ideal for studying mini-Neptune worlds. Planetary atmospheres act like cosmic filters that absorb specific colors of starlight passing through them. This creates atmospheric fingerprints that reveal chemical composition. Transit spectroscopy analyzes how starlight changes as it filters through planetary atmospheres during transit events. Different atmospheric gases absorb different wavelengths of light. Water vapor absorbs infrared light at specific wavelengths. Methane creates distinctive absorption features. Hydrogen and helium remain nearly invisible to most observations. The technique requires extremely sensitive instruments because atmospheric absorption signals are incredibly weak. Detecting these signals pushes current technology to its limits. Atmospheric fingerprinting provides the only direct method for studying the chemical composition of distant planetary atmospheres from Earth. Planets emit their own infrared radiation based on their surface and atmospheric temperatures. This thermal emission provides information about planetary heat distribution and circulation. Thermal radiation observations measure the heat glow that planets emit into space. Hot planets glow brighter in infrared light than cool planets, following the same physics that makes hot stoves glow red. The observations reveal day-night temperature differences that indicate atmospheric circulation strength. Strong atmospheric circulation evenly distributes heat. Weak circulation creates extreme temperature contrasts. Measuring thermal emission requires space-based infrared telescopes because Earth's atmosphere blocks most infrared light from reaching ground-based observatories. Heat signature mapping helps astronomers understand atmospheric dynamics and energy balance on worlds with no solar system equivalent. Planets show different faces to telescopes as they orbit their host stars. These changing viewing angles create brightness variations that reveal atmospheric and surface properties. Phase curve observations measure how planetary brightness changes throughout complete orbital cycles. The technique resembles tracking how moon phases change but operates on distant worlds. The brightness variations indicate whether planets have thick atmospheres that redistribute heat or thin atmospheres that create stark temperature differences between day and night sides. Some planets show brightness peaks when their hot day sides face toward Earth. Others maintain constant brightness if thick atmospheres even out temperature differences. Phase curve analysis provides insights into atmospheric circulation patterns and thermal properties that other techniques cannot access. Transit events don't always occur exactly when predicted. These timing variations indicate gravitational perturbations from additional planets in the same system. TTV analysis stands for transit timing variations and measures how transit schedules deviate from perfectly regular patterns. The deviations reveal gravitational influences from unseen planetary companions. The timing changes occur because multiple planets gravitationally tug on each other. slightly altering their orbital periods over time. These gravitational interactions create detectable patterns in transit timing. The technique can discover planets that never transit their stars directly. It's particularly sensitive to planets in orbital resonances, where gravitational interactions become amplified. TTV analysis has revealed numerous multi-planet systems and helped astronomers understand how planetary systems organize their orbital architectures. Astronomers work backward from observed light spectra to determine atmospheric temperature, pressure, and composition profiles. This reverse engineering process reconstructs three-dimensional atmospheric structures. Atmospheric retrieval uses computer models to match theoretical atmospheric predictions with actual telescope observations. The technique systematically tests different atmospheric scenarios until finding the best match. The process resembles solving complex puzzles where astronomers must determine atmospheric properties that produce the observed spectral signatures. Multiple atmospheric combinations can sometimes explain the same observations. Retrieval analysis provides detailed atmospheric profiles, including temperature variations with altitude, chemical abundance patterns, and cloud layer properties. This computational approach transforms raw spectral data into comprehensive atmospheric portraits that reveal the three-dimensional structure of distant worlds. The Hubble Space Telescope revolutionized planetary atmosphere observations by providing stable, high-precision measurements impossible from Earth's surface. This space-based observatory eliminated atmospheric interference that plagued ground-based studies. ACE-T observations avoid the blurring and absorption effects of Earth's atmosphere that limit ground-based telescopes. The space environment provides rock-steady pointing and consistent measurement conditions. Hubble's instruments can measure incredibly subtle atmospheric absorption features in the spectra of transiting planets. The telescope's precision enabled the first reliable detections of water vapor in exoplanet atmospheres. The observatory's long operational lifetime allows systematic studies of multiple planets using identical instrumental setups. This consistency enables direct comparisons between different atmospheric systems. Hubble's atmospheric discoveries established the foundation for more advanced space-based studies with newer, more powerful observatories. The James Webb Space Telescope transforms atmospheric studies by observing infrared wavelengths that reveal previously invisible atmospheric components. This new capability opens entirely new windows into planetary atmospheric chemistry. JWST operates at infrared wavelengths where many atmospheric molecules create their strongest absorption signatures. Water vapor, carbon dioxide, methane, and other gases show clear spectral features in infrared light. The telescope's enormous mirror and advanced instruments provide sensitivity improvements of 10 to 100 times over previous space observatories. This allows detection of trace atmospheric components and cloud properties. Infrared observations penetrate deeper into atmospheric layers than visible light studies. This reveals atmospheric structure and composition at multiple altitude levels. Webb's infrared vision is revolutionizing our understanding of atmospheric diversity and chemical processes operating on worlds throughout the galaxy. Networks of ground-based telescopes work together to discover and characterize thousands of planetary candidates. These coordinated survey programs provide the statistical foundation for understanding planetary populations. Ground-based surveys use multiple telescopes simultaneously to monitor thousands of stars continuously. Automated systems identify potential transit events and coordinate follow-up observations. The telescope networks can confirm planetary discoveries and measure basic properties like orbital periods and planetary sizes. They provide the bulk discovery capability that space missions cannot match. Survey telescopes typically use smaller, less expensive instruments than flagship space missions, but their large numbers and continuous operation make them incredibly productive for planetary discovery. These ground-based networks create the comprehensive planetary census that reveals how common mini-Neptune worlds are throughout the galaxy. Not every brightness dip or spectral signal indicates a genuine planetary detection. Statistical validation techniques distinguish real planetary discoveries from instrumental artifacts and astrophysical false positives. Statistical validation uses multiple independent lines of evidence to confirm planetary interpretations. The process eliminates explanations that don't require actual planets orbiting distant stars. Common false positives include binary star systems, variable stars, and instrumental problems that can mimic planetary signals. Each potential explanation must be systematically ruled out. The validation process combines observational data from multiple instruments and techniques. Transit photometry, radial velocity measurements, and direct imaging all provide independent confirmation methods. Statistical validation ensures that claimed planetary discoveries represent genuine worlds rather than measurement errors or misinterpreted astrophysical phenomena. One mini-Neptune sits closer to Earth than any other example of its kind. This proximity makes it the most intensively studied world in its entire planetary category. GJ1214b orbits a small red dwarf star just 47 light-years from our solar system. In cosmic terms, this represents our immediate neighborhood. Most other mini-Neptunes lie hundreds or thousands of light-years away. The planet's close location allows telescopes to gather detailed atmospheric data that would be impossible for more distant worlds. Astronomers can study its atmosphere with precision unavailable anywhere else. Multiple space telescopes have targeted this world repeatedly. Each observation adds new details about its atmospheric composition and thermal structure. GJ1214b serves as the prototype that defines our understanding of how these atmospheric worlds actually behave in space. A remarkable world exists in the temperature zone where liquid water could theoretically survive on planetary surfaces. This location makes it one of the most intriguing mini-Neptune discoveries. K218b orbits within its star's habitable zone, the region where temperatures allow liquid water to exist. Most mini-Neptunes orbit too close to their stars and scorching surface conditions. Telescope observations have detected clear water vapor signatures in this planet's atmosphere. The spectral fingerprints show unmistakable evidence of H2O molecules throughout its atmospheric layers. The water detection doesn't guarantee liquid oceans exist on the surface. Thick atmospheric layers might prevent any liquid water from forming below the gas envelope. But K218b represents our best example of a potentially habitable mini-Neptune that maintains water in some form within its atmospheric system. Extreme conditions can create planetary environments that exceed anything in our solar system. One mini-Neptune experiences temperatures hot enough to melt solid rock into flowing lava oceans. 55 Cancri orbits so close to its host star that surface temperatures reach 4,000 degrees Fahrenheit. This heat transforms the planetary surface into a molten hellscape of liquid rock and metal. The planet likely maintains vast lava oceans that continuously circulate beneath its thick atmosphere. Imagine Earth's surface completely melted into flowing rivers and seas of molten rock. Thermal observations reveal dramatic temperature differences between the planet's day and night sides. The day side glows white-hot, while the night side remains merely red-hot. This extreme world demonstrates the incredible range of conditions that mini-Neptunes can experience depending on their orbital distances from host stars. Most mini-Neptune atmospheres contain thick cloud layers that hide their internal composition from telescopes. One remarkable exception provides unprecedented visibility into atmospheric chemistry. At 8P11b possesses an unusually clear atmosphere with minimal cloud formation. This transparency allows starlight to penetrate deep into atmospheric layers without obstruction. Spectroscopic observations reveal strong water vapor absorption features throughout this planet's atmosphere. The clear conditions provide the clearest water detection ever achieved for any mini-Neptune world. The absence of high-altitude clouds suggests unusual atmospheric chemistry or circulation patterns that prevent normal cloud condensation processes. ATP11MB offers astronomers their best window into mini-Neptune atmospheric composition because its clear skies eliminate the opacity problems that plague most other examples. Some worlds achieve such low densities that they seem to barely hold together at all. One mini-Neptune resembles cosmic cotton candy in terms of its incredibly fluffy structure. WASP-107b has a density lower than cork or styrofoam. If you could somehow place this planet in a cosmic ocean, it would float like a giant beach ball. The ultra-low density indicates an enormous atmospheric envelope surrounding a relatively small solid core. The atmosphere might contain 90% of the planet's total volume while contributing only a small fraction of its mass. This extreme fluffiness challenges our understanding of how planets maintain structural integrity. The gravitational forces holding this world together seem barely sufficient. WASP-107b represents the extreme end of atmospheric inflation that's possible for mini-Neptune worlds before they become completely unstable. Atmospheric loss processes can strip away entire planetary envelopes, revealing the solid cores hidden beneath. One remarkable world provides a glimpse of what lies inside these atmospheric giants. TOIA-49b appears to be a former mini-Neptune that completely lost its hydrogen-helium envelope. What remains is a bare rocky core with roughly the same composition as a super-Earth. The planet's size and mass suggest it originally possessed a massive atmospheric shell. Intense stellar radiation and atmospheric escape processes gradually removed all gaseous material over cosmic time. This stripped world offers direct evidence that mini-Neptunes can evolve into rocky super-Earths through atmospheric loss. The process leaves behind the solid planetary cores that were hidden beneath thick gas envelopes. TOI-8049b serves as a cosmic archaeology site where astronomers can study the solid foundations that support mini-Neptune atmospheric structures. Some mini-Neptunes might contain vast amounts of liquid water hidden beneath their atmospheric envelopes. One intriguing world shows characteristics consistent with this water world scenario. Kepler-13a displays properties suggesting it contains significant liquid water either as surface oceans or as high-pressure liquid layers within its interior structure. The planet's density measurements indicate substantial amounts of lighter materials that could represent water in various forms. Ice, liquid water, and water vapor might all coexist within different regions. If confirmed, this would represent an entirely new category of planet with no equivalent in our solar system. Imagine worlds where water comprises a major fraction of total planetary mass. Kepler-13a demonstrates that mini-Neptunes might create environments capable of maintaining liquid water in ways completely different from terrestrial planets. Some planetary discoveries provide exceptionally accurate measurements that serve as reference points for understanding entire planetary categories. One nearby Mini-Neptune offers unprecedented precision. 8D219134c orbits close enough to Earth that astronomers can measure its properties with extraordinary accuracy. Both its mass and radius are known to within tiny error margins. The precise measurements make this planet a benchmark for testing theoretical models of Mini-Neptune internal structure and atmospheric properties. Its well-determined characteristics help calibrate the techniques astronomers use to study more distant and less precisely measured examples of similar worlds. HD219134c functions as a cosmic measuring stick that helps astronomers understand the fundamental properties shared by all Mini-Neptune worlds. Mini-Neptunes rarely exist in isolation. Many participate in complex multi-planet systems where gravitational interactions influence their evolution and orbital characteristics. L9859c belongs to a tightly packed planetary system containing multiple small worlds orbiting very close to their host star. The planets interact gravitationally throughout their orbital cycles. These gravitational interactions provide insights to how planetary systems organize themselves during formation. The orbital architecture reveals clues about migration processes and formation timescales. Multi-planet systems like this one demonstrate that Mini-Neptune formation often occurs alongside other planetary types within the same stellar nursery environment. L9859c illustrates how individual planetary characteristics depend on the broader system context in which these worlds form and evolve. The most famous multi-planet system contains 7 worlds, some of which display Mini-Neptune characteristics. This system provides a natural laboratory for comparing different planetary evolution pathways. TRAPPIST-1 hosts 7 planets orbiting a small red dwarf star. Several of these worlds fall into the Mini-Neptune size category, while others resemble rocky super-Earths. The system's compact architecture allows direct comparison between different planetary types that formed under nearly identical conditions. This reveals how small differences in formation can produce dramatically different outcomes. Some planets retained thick atmospheres, while others lost their gaseous envelopes. The diversity within a single system illuminates the factors controlling atmospheric evolution. TRAPPIST-1 serves as a Rosetta Stone for understanding how stellar environment and formation conditions determine final planetary characteristics. Some planetary systems organize themselves into precise orbital relationships, where planetary periods maintain exact mathematical ratios. These resonant configurations reveal underlying gravitational architecture. TOI 270 contains multiple Mini-Neptune worlds locked in orbital resonances where their orbital periods maintain precise 3:2 and 2:1 ratios. The planets complete their orbits in synchronized patterns. These resonant relationships indicate that the planets migrated inward together while maintaining gravitational coordination. The process requires specific conditions during planetary system evolution. The orbital synchronization stabilizes the system against disruption and provides evidence for smooth migration processes rather than violent gravitational interactions. TOI 2270 demonstrates how Mini-Neptune systems can achieve stable, long-term configurations through careful orbital choreography maintained by gravitational forces. The closest star system to Earth contains its own Mini-Neptune world. This proximity makes it a prime target for future direct imaging missions, that could photograph planetary surfaces. Proxima Centauri C orbits our nearest stellar neighbor at a distance of just 4.2 light-years. No other mini-Neptune exists closer to our solar system. The planet's nearby location makes it accessible to future space missions equipped with advanced direct imaging capabilities. Telescopes might eventually photograph this world directly rather than detecting it through indirect methods. Direct imaging could reveal surface features, atmospheric structure, and chemical composition with unprecedented detail. This would provide insights impossible to achieve through current transit and radial velocity techniques. Proxima Centauri Phi represents the most promising target for detailed mini-Neptune characterization using next-generation observational technologies. Could life exist under crushing hydrogen atmospheres on worlds completely unlike Earth? A new category of potentially habitable planets challenges our assumptions about where life can survive. Hycean worlds represent mini-Neptunes with thick hydrogen atmospheres covering deep liquid water oceans. The name combines hydrogen and ocean to describe these exotic environments. The hydrogen atmosphere acts like a cosmic blanket that traps heat and maintains liquid water temperatures even far from the host star. Pressures at the ocean surface might reach 100 times Earth's atmospheric pressure. Life in these environments would face conditions completely unknown on Earth. High pressure, hydrogen-rich chemistry, and perpetual darkness create challenges no terrestrial organism has ever encountered. These worlds expand the potential habitable zone around stars by maintaining liquid water through atmospheric greenhouse effects, rather than stellar heating alone. Thick atmospheres can trap enormous amounts of heat and create surface conditions warm enough for liquid water. This greenhouse effect operates much more powerfully than anything Earth experiences. Greenhouse heating occurs when atmospheric gases absorb infrared radiation and prevent planetary heat from escaping into space. The trapped energy accumulates and raises surface temperatures. Mini-Neptune atmospheres contain thousands of times more gas than Earth's atmosphere. This creates greenhouse effects so powerful they can maintain liquid water temperatures even on planets orbiting far from their stars. The effect becomes self-reinforcing as water vapor adds additional greenhouse warming. More atmospheric heating produces more water vapor, which produces even stronger greenhouse effects. Atmospheric greenhouse heating could make mini-Neptunes habitable at orbital distances where rocky planets would freeze solid and remain lifeless. Astronomers have identified specific orbital distances where planetary surface temperatures allow liquid water to remain stable. This habitable zone sets the boundaries for potential life-supporting worlds. The habitable zone represents the range of orbital distances where stellar heating provides just enough energy to maintain liquid water on planetary surfaces. Too close, and water boils away; too far, and everything freezes. For mini-Neptunes, the habitable zone extends much farther from stars than for rocky planets. Thick atmospheres can maintain liquid water at orbital distances where Earth-like worlds would become frozen wastelands. The zone boundaries depend on stellar type and atmospheric properties. Cool red dwarf stars have narrow habitable zones. Hot blue stars create wide temperature ranges where life might survive. Identifying habitable zone mini-Neptunes provides the first step in searching for potentially life-supporting worlds beyond our solar system. Certain atmospheric gases serve as potential indicators of biological activity. These biosignature molecules could betray the presence of life on distant worlds through spectroscopic observations. Biosignature detection involves searching for atmospheric chemicals that living organisms produce, but that don't occur naturally through geological processes alone. Oxygen represents the most famous biosignature because it reacts quickly with other atmospheric components. Large amounts of atmospheric oxygen suggest ongoing biological production to replace what chemical reactions consume. Methane provides another potential biosignature. Especially when detected alongside oxygen, this combination creates chemical instability that requires continuous production from biological sources. The simultaneous detection of multiple biosignature gases would provide compelling evidence for biological activity operating on distant Mini-Neptune worlds. Research into Earth's most extreme environments reveals life thriving under conditions once thought impossible. These discoveries expand the range of conditions where life might exist on alien worlds. Extremophile organisms live in environments that would kill most other life forms. They survive in boiling water, freezing ice, crushing pressures, and highly acidic or alkaline conditions. Some Earth organisms thrive in high-pressure environments similar to conditions that might exist on Mini-Neptune surfaces. Others survive in hydrogen-rich environments that resemble these worlds' atmospheric compositions. The study of extremophiles provides biological precedents for life surviving under Mini-Neptune conditions. If organisms can adapt to extreme Earth environments, similar adaptations might occur on alien worlds. Extremophile research guides our understanding of which Mini-Neptune environments might realistically support biological activity. Living systems require stable environmental conditions maintained over geological timescales. Atmospheric stability becomes crucial for any life that might evolve on Mini-Neptune worlds. Atmospheric stability refers to a planet's ability to maintain consistent temperature, pressure, and chemical composition over billions of years. Rapid environmental changes would prevent complex life from establishing itself. Planets must retain their atmospheres against stellar radiation, atmospheric escape, and other loss processes. Worlds that lose their atmospheres quickly would become uninhabitable before life could develop. The stability also requires protection from extreme stellar activity like flares and coronal mass ejections. Strong magnetic fields or thick atmospheres could provide this protection. Long-term atmospheric stability represents a fundamental requirement that eliminates many otherwise promising Mini-Neptune candidates from consideration as potentially habitable worlds. Future space telescopes will photograph planets orbiting other stars directly rather than detecting them through indirect methods. This direct imaging capability will revolutionize our understanding of Mini-Neptune characteristics. Direct imaging involves separating planetary light from the much brighter light of host stars. This requires advanced telescope technology and sophisticated image processing techniques. Current telescopes can only study planets through transit observations and radial velocity measurements. Direct imaging would allow astronomers to observe planetary surfaces, atmospheres, and orbital motion directly. The technique could reveal seasonal changes, weather patterns, and atmospheric composition variations that indirect methods cannot detect. Surface features and atmospheric structure would become directly observable. Direct imaging represents the ultimate goal for characterizing potentially habitable Mini-Neptune worlds with unprecedented detail and accuracy. Specialized instruments can block starlight while preserving the much fainter light from orbiting planets. This coronagraph technology makes direct planetary imaging possible from space-based observatories. Coronagraph instruments use precise optical techniques to suppress starlight by factors of billions while maintaining sensitivity to nearby planetary light sources. The technology resembles eclipse observations, where the moon blocks solar light and reveals the sun's corona. Artificial coronagraphs create similar effects using carefully designed optical components. Advanced coronagraphs combine multiple light-blocking techniques including masks, interferometry, and adaptive optics to achieve the contrast ratios needed for planetary detection. This starlight suppression technology will enable the first direct photographs of mini-Neptune atmospheres and potentially reveal signs of habitability or biological activity. Several major space missions currently under development will focus specifically on characterizing potentially habitable worlds. These observatories will provide unprecedented capabilities for studying mini-Neptune atmospheres. The Nancy Grace Roman Space Telescope will demonstrate coronagraph technology and directly image giant planets orbiting nearby stars. This mission will test the techniques needed for studying smaller worlds. Ground-based telescopes like the 30-meter telescope will provide enormous light-collecting power for detailed spectroscopic studies of mini-Neptune atmospheres. Future space missions specifically designed for exoplanet characterization will combine direct imaging with advanced spectroscopy to study atmospheric composition, temperature structure, and potential biosignatures. These next-generation observatories will transform mini-Neptune studies from basic discovery science into detailed characterization of potentially habitable alien worlds. The study of mini-Neptune habitability is creating entirely new fields of astrobiology research. These worlds represent potential habitats completely different from anything in our solar system. Astrobiology traditionally focused on Mars-like or Earth-like environments where life might exist on rocky planetary surfaces. Mini-Neptunes require completely different biological and chemical models. The atmospheric chemistry, pressure conditions, and energy sources available on these worlds create novel environments where life might evolve along completely different pathways. Understanding mini-Neptune habitability requires interdisciplinary research combining astronomy, biology, chemistry, and planetary science in unprecedented ways. The astrobiology revolution sparked by these worlds is expanding our definition of habitability and creating new frameworks for understanding how life might arise and thrive throughout the universe.